8.8, solving radical equations and inequalities. The learning goals: students will solve radical equations and radical inequalities. For solving radical equations, there are 3 steps. First, isolate the radical if it's not already isolated. 2, raise each side to an exponent equal to the index of your radical, or of your rational exponent, the denominator, and solve. Step 3, check for extraneous solutions. Any value derived from your original problem that does not solve that original. For the first example, keeping the first step in mind, we need to isolate the radical as if it was a variable. So that square root of x plus 1 we want by itself, subtract 5 from both sides, so that the square root of x plus 1 equals 11. What is the index implied to be? It is the square root of x plus 1, tells us our index is 2. Raise both sides of your radical equation by that index. When you square both sides, on the left-hand side, you'll get x plus 1, and on the right-hand side, you'll have 121. Solving for x by subtracting 1, x is 120. That derived value may be an extraneous solution. For these problems, you must check, because when you square it, you're actually putting an additional copy of your variable into the problem that wasn't originally there. So you might create something of an extraneous solution. When we check, we just substitute back in either here or here, anywhere before you raise both sides by the index of your radical. We have 120 plus 1 for our radicand, and we want to know, is that equal to 11 after we take the square root? It is. So in solution set notation, 120. Remember, first step, isolate the radical. You want to do that before you square, because then you're going to have to distribute your square root, and then you're going to make more of an issue in the example. For the second example, to isolate the radical, we need to divide both sides by its coefficient of 7, leaving us with the cube root of the radicand, 5x minus 7, is equal to 12. 7 goes into 70 10 times. 7 goes into 14 twice, and 10 plus 2 is 12. Notice our index this time is 3. Raise both sides by that index to eliminate the radical. And remember why that works. The cube root of something is saying that you're raising it to the 1/3 power. So if you raise it to the 3rd power, you get to multiply your exponents of 1/3 and 3 to get to the 1st power. On the left-hand side, we have 5x minus 7. And on the right-hand side, don't worry about doing this without a calculator. It's going to be 1,728. The reason why I picked a larger number here was so that you wouldn't immediately see that 7 evenly divided 84 in the original problem. We add 7. 5x equals 1735. And divide both sides by 5, x equals 347. Don't forget to check. Sometimes your problem will have no solution, or not all derived values will be part of the solution. So we take the cube root of 5 times 347. I'm just substituting in here. And minus 7 as the finished radicand. And does that equal 12? I used a calculator, to be honest. Took the square root, and it equaled 12. For our solution set, 347. In these first 2 examples, we worked with the square root. We had to subtract 5 from both sides before raising both sides by the index. In the second example, we had to divide by 7 before raising both sides by the third power because we're working with a cubed root. Feel free to pause at any time. With this example, you can't isolate a single radical because there's one on each side, but they are as isolated as possible. So you take a look at your index. You're working with square roots, so the index is 2. So you're going to raise both sides to the second power. Notice I include the coefficient of 3 on the right-hand side of the equation in my squaring. The left-hand side is just the radicand, 7x plus 2. The right-hand side, I have to use the product of powers property. 3 squared is 9, and then the square of a square root is the radicand. Careful, use parentheses. I distribute the 9 on the right-hand side. Subtract 27 from both sides. Subtract 2 from both sides. And divide by negative 20. X is 1. Just make sure we're all on the same page. Back in this original part of the problem, when I raise both sides to the second power, I use parentheses so that on the right-hand side I use the product of powers property, 3 squared, and then the square root of 3x minus 2 as a quantity squared. I need to check. Substitute the 1 back in to the original problem that I'm pointing to with the red arrow. So 7 times 1 plus 2. I want to know if that is equal to 3 times the square root of 3 times 1 minus 2. On the left-hand side, I have the square root of 9, which is 3. On the right-hand side, my radicand is 3 minus 2, or the square root of 1. And we have equality. Therefore, our solution in solution set notation is 1. So notice here, I didn't set one side equal to 0. So I didn't get on one side of the equation all of the terms with radicals. You just have them as isolated as possible. So one of the radicals owns one side of the equation, and one of the radicals owns the other side of the equation. And then you raise both sides by the index. With the fourth example, the radical is isolated. Step 1 is completed. On the right-hand side, we're going to square a binomial, so we'll have to be careful. Our index is 2, so we'll raise both sides to the second power. On the left, we simply get the radicand, negative 3x plus 33. On the right-hand side, it wouldn't hurt to write the binomial multiplied by itself twice, or write 2 copies of the binomial to be explicit about that you're squaring it, so you'll need to factor, rather distribute. So we got that going on here. Because we're squaring a binomial, there's a shortcut. You take the first term of the binomial 5 and you square it, and that's 25. You take the product of the 2 terms in the binomial, 5 times negative x is negative 5x, and then you double that for negative 10x. And then you take the second term in your binomial and you square it. Negative x as a quantity squared is positive x squared. Of course, you could go through the distribution to find your 4 terms and then combine the inner and outer products. We want to set this equation equal to 0 because I have I'm anticipating a quadratic, so I'll want to factor or use the quadratic formula or completing the square. So I'll set the left-hand side equal to 0 since I realize my square term is on the right-hand side and is positive, and I'll let that lead the way. I'm going to add 3x to both sides. So on the right-hand side, it's going to be 3x minus 10x for a net of negative 7x. And then I'm going to subtract 33 from both sides. 25 minus 33 is negative 8. Hopefully right away you see that you could factor. The factors of negative 8 that give you negative 7 are negative 8 and positive 1. So they multiply to negative 8, but add to the middle term negative 7. And you set each of these factors to 0 using the zero product property, and you get your values of x as -1 and 8. So you change the signs of your constants and divide by any coefficient in front of your x. Let's check. Substitute in -1 into the original problem. -3 times -1 plus 33. Does that equal 5 minus the -1? Okay, my radicand is -3 times -1. So that's +3, then plus 33 for a radicand of 36. The square root of that is 6. And on the right-hand side, subtracting a negative is addition. 5 plus 1 is 6. We have equality. That'll be part of our solution. For the next value of 8, we substitute in. We have -3 times 8 plus 33. Now, that is not going to equal 5 minus 8. Because we're going to, on the left-hand side, have -3 times 8, which is -24. I'm sorry. -24 plus 33. So it's a positive number that we're going to take the square root of. But it's going to be the square root is equal to -3. And that can't happen if you're staying in the set of real numbers. So that's not the case. So our only solution is -1. So to write down what I was talking about, the square root cannot equal a negative unless you're working in the set of complex numbers. We're restricting ourselves to the set of reals. Go ahead and turn the page over. Notice we are representing our rational exponent using the 1/3 instead of the cubed root. The idea is still the same. Think about the denominator of 3 as your index that you'll raise to both sides. So the denominator of your rational exponent is equal to your index. Let's raise both sides to the 3rd power. On the left-hand side, we get the base of 5x plus 7 because 1/3 times 3 is 1, so we raised it to the 1st power, not changing it. And on the right-hand side, we know the perfect cube. 3 cubed is 27. Subtract 7 from both sides. 5x is 20. And dividing out 5, x is 4. Make sure to check. Substitute into the original. 5 times 4 plus 7 to the 3rd. We want to know, is that equal to 3? We have 5 times 4 is 20, plus 7 is 27. Its cubed root, or when it's raised to the 1/3 power, equals 3. Our solution is 4. We've seen several different ways to encounter radical and rational equations. You always raise both sides to the index after you isolate the radical. For radical inequalities, it'll be much of the same, but there's a new first step. And that's to set the radicand greater than or equal to 0 and solve that inequality. There are going to be 2 steps, just like when we worked with LCDs and inequalities a couple sections ago where you had to consider the case of the denominator. Here we always want to make sure that we're in the set of real numbers, so we have to think about kind of like the domain values of x, and that'll be step 1. And then step 2 will be to solve the original inequality as it stands. I always like students to do step 1 first, where they set the radicand, in this case the 2x minus 6, greater than or equal to 0, so they don't forget. Add 6 to both sides. 2x is greater than or equal to 6. And after dividing both sides by 2, x is greater than or equal to 3. That's part of your compound inequality. Step 2 is solve the original. I'll rewrite it for you. You have the square root of 2x minus 6 plus 3 is less than or equal to 9. Subtract 3 from both sides, giving you 2x minus 6 is less than or equal to 6. We've successfully isolated the radical. Its index is 2. We square both sides. No need to change the direction of the inequality. We're not multiplying or dividing both sides by a negative. We get the radicand 2x minus 6 on the left, and that's less than or equal to 36 on the right. Add 6. 2x is less than or equal to 42. Divide by 2. X is less than or equal to 21. And now we use a compound inequality. Think about it. X, you don't have to do the number line, but just to show you what I'm thinking, we start at x is 3 and go to the right. And then we have x is 21. And then we're going to the left. And so then our compound inequality for the solution is the intersection. So it's a set of all numbers, real numbers x, such that x is greater than or equal to 3 and less than or equal to 21. Tonight you're going to do the review assignment for the chapter, which will be due tomorrow for the half day, and we'll go over it, and then we'll review Thursday and Friday for Monday's test.